Hey everyone, how's it going? It's Mr. Johnson here. We're going to go over electricity today, and this is actually going to be a two-part series. We'll try to make the second part nice and quick. First part, I'll kind of talk about some of the terminology that has to do with electricity, and then the second part, we'll talk about electricity calculations, known as Ohm's law calculations, which will be an important part of your test. All right, so here we go. Atoms. Pretty clear stuff here. I'm not going to go too in-depth into this. Hopefully at this point you know this. If not, that's probably something you should take a look at. Um, Atoms have protons, neutrons, and electrons. Protons are positive and electrons are negative. Electrons, where are they located? They are not in the nucleus. They are on the outer edges of the atom and they can move. So something important to know, and this is the fundamental understanding of electricity, is the positive charge in an atom, the protons, they don't move. They're going to stay in the nucleus. The only time I can think of, and I'm sure there's more examples, of when a proton would actually end up leaving the nucleus would be in alpha decay, which we just talked about. But for the most part, atoms or protons are going to stay in the nucleus. Electrons are going to be on the outside, and they actually can be easily moved. And that's essentially what electricity is the movement or the flow of those electrons. So a concentration of electrons in an atom gives a net negative charge. So if an atom, and again, typically we said electrons and protons are going to have the same amount. But if we're looking at it, if an atom has a lot of electrons concentrated in it, it is going to be negatively charged. If the electrons are gone, so again, protons aren't going to necessarily leave or come into the atom. If we have electrons leaving, if they are removed from the atom, it's going to be more positively charged. Now I think I actually did the research this time. I think I can move this down to here now, and we should be good for the rest of the video. So the world is filled with electrical charges all around us. One common example I think of is when I was younger. Unfortunately, my older brother showed me my first lesson in charges all around us. He used to, he would he would put on fuzzy socks, and um, he would go up to like a carpet or a rug or something, and he would find a way to build up those electrons, and then he would actually shock me and would transfer those electrons. So I'm well aware. Another good example of this, I don't have one. Maybe I could show you in the next video, but a balloon. If you charge a balloon, it's going to gain or lose electrons. So we have potential energy. We talked about first trimester, and potential energy is stored energy. And we specifically looked at mechanical or gravitational potential energy. In this particular unit, we're looking at static electricity as our potential energy, meaning these, we have a charge built up, positive or negative. We have this charge built up. And when we have that buildup, eventually we are going to be able to transfer those electrons. And that is when you get shocked, or, you're opening your locker in the wintertime and you touch the metal and it shocks you. So static electricity is the buildup of an electrical charge on the surface of an object. The charge builds up but does not flow, meaning it's there. Those electrons are there. The charge is building up. It's not leaving, though. It is not going to something else. So static electricity is potential, meaning it is not going to move, it is stored. And that's kind of something that I've already talked about. But essentially, think of static electricity as electricity isn't moving. It is just still buildup of electrons. And I was wrong. Turns out I cut off some of the words. So a discharge, if we build up a charge, a discharge is when there's a loss of static electricity due to three possible things. Could be friction, could be conduction, and it could be induction. And unfortunately, we're not in class, but we actually have a pretty cool demonstration, and maybe we'll post a resource or something like that you can watch. But essentially, these are kind of the three ways that we can transfer those electrons. And we can talk kind of about that. But essentially, you're going to feel it. If that electron transfer does happen, you will get shocked, or someone else will get shocked. It's a thing. So again, conduction just means like directly touching like metal and getting shocked. Induction would be through an electrical field. You're not necessarily touching the object, but you can still get shocked. And friction would be specifically like rubbing your feet like on the ground and building up a charge, and then eventually, yeah, losing charge through the friction. So electricity that moves is known as the term current. Current's a very important word. I would circle it. I would underline it. I would do what you need to do. Current is going to be the flow or the rate of electrons from one place to another. So something important to keep in mind about this definition is the flow is kind of like a river. A river has current, and the current is the flow of water. In this case, current and electricity is the flow of electrons. So that's kind of what I use to think about it. The greater the current, the actually, the faster those electrons are moving, essentially. We measure it in amps or amperes. We're just going to say amps for the most part. So we will be doing calculations, believe it or not, with this particular unit, and we would measure current in amps. And it's a kinetic energy, meaning it's moving. It's the flow. It is not static. It is moving. So how do we control currents? This happens in our houses. We control them with circuits. A circuit is going to be a path for the flow of electrons. Typically, we use wires, and we use wires that are going to do a pretty good job of conducting electricity. So maybe like a copper wire is a typical example we would see. But essentially, current or circuits are going to be the path in which they flow. And we'll talk a little bit about two different types of currents, and Mr. Overgaard is going to take you through a virtual lab where we actually look at those currents. But for now, I guess what you need to know is a circuit is like the path which those electrons are going to flow. Two types of currents. We have direct current, abbreviated DC, where electrons are going to flow in the same direction in a wire. So unfortunately, this doesn't move, but essentially think of it as, if you can see my mouse here, it's going to flow in only one direction and one direction only. So that's a direct current. Now, the other kind is going to be essentially the opposite of a direct current. Instead of flowing in the same direction, they're going to flow in different directions. So sometimes maybe the electrons are flowing this way. Sometimes maybe they're flowing that way. We are going to have alternating current. So I guess a good example of this would be like if you look at like a water pump, essentially, like it's pushing water one way and then it kind of releases, and then the water is going to go back down, and then it pushes it again, goes up, and then releases, and it's going to go back down. Basically, meaning we're going to have two different air paths or multiple paths in which the electricity can flow. In this case, alternating current, AC. So DC, same direction. Alternating current, AC, is going to be potentially different directions. All right, two types of circuits as well. So essentially, we talked about the two types of circuits, but we're going to kind of go into specifically the two names of the types of circuits that we would have. We have a series circuit, and we will talk about the other one later. A series circuit is saying that all of the components are lined up along just one path. If we break one circuit, all the components are turned off. So, oh man, here I have to move my picture here. So if we look at this particular current right here, or circuit right here, we see that there is only one path in which the electrons are going to flow. So a series circuit just means, one path in which the electrons can travel. If I turn off this, say there's a light switch right here, I turn off this light switch, there is no power going to these 4 light bulbs. They are all going to turn off. Now we can see with the second type of circuit, and I'm sorry, I'm going to have to move my face a whole lot during this presentation. Essentially, a parallel circuit is the other one that we are going to look at. A parallel circuit is where there are several branching paths to the components. If the circuit is broken at any one branch, only that component is going to turn off. So, essentially, think of your house. When I turn my bedroom light off, that's not necessarily going to turn off all the lights in the house. Parallel circuit, great example is your house. I turn off my bedroom light, the living room light's still on, my roommate's bedroom light is still on, whatever. That is a parallel circuit. There are multiple branches. So if we look at what it looks like, here it is right here. This is an example of a parallel circuit. If I was to turn off this particular light switch right here, these 3 lights are still going to shine. Just this one will not be shining. So this one works, this one works, this one works. That's kind of the way it goes. If I were to turn off this light, the other 3 still could remain on. All right, conductors versus insulators. I'm sure we've heard of these words before. Now think to yourself, what is something that does a good job of conducting electricity? Typically, some of the thoughts are we have metals are a big one. Um, some people would like to say water, which I kind of agree with that. Water typically is not a good conductor unless we add basically salt to it. So if we add salt or we add ions, they're called, water is very conductive. So our body is covered in salt, meaning that if we were to sit in the bathtub, and don't try this at home, someone drops the hairdryer in the bathtub, it's potentially really bad because our body is going to be a great conductor of electricity. Now, insulators are materials where electrons cannot move through. Some good examples of this are a balloon, rubber. Rubber does not do a good job of conducting electricity. You're not going to get shocked if you're wearing like a rubber suit, I guess. Electricity does not want to move through that. Some other good examples are, think about like a tree. Yes, trees can get struck by lightning, but essentially, electricity is not going to do a great job moving through something that it doesn't have easy ability to move through. So there are some examples there. I just kind of went over those. Paper and plastic, 2 other great examples that just really don't conduct electricity well. Styrofoam does not conduct electricity well. That's just kind of the way it is. That's the way electricity works. And we could get into the chemistry behind that, but ultimately we're not necessarily going to do that right now. So we've talked about current. Current is the flow of electrons. Resistance is going to be the opposition to the flow. So current and resistance are directly related, but they kind of counter each other. If we have more resistance, the current's going to typically be lower. If we have less resistance, the current is going to be much higher. Same goes, other way around. More current, less resistance. Less current, more resistance. So I would really take a look at that. This second bullet point here, current, resistance kind of oppose each other. So when we have lots of resistance, typically we are going to have something called heat. So an example in real life, and this is kind of an interesting one. This is my phone charger right here. Um, Actually, this box, if you can see this box, this is going to be where the resistance is. This wire is kind of like where the electrons are flowing. They are flowing through this wire. However, when I plug it into a wall, if I leave my phone plugged into the wall for too long, what do I feel on my charger? Usually I feel a little bit of heat. This box is where most of the resistance is. Yes, there's a little bit of resistance in the wire already, but this box is really what prevents, like a house fire, for example. And this is a good reason if any of you ever travel to Europe, you need to be extra careful because they actually have strong, higher voltage outlets. And sometimes our phone chargers or our resistors don't necessarily do a good job countering that higher voltage. And we'll talk more about that in our second video. But essentially, good thing to keep in mind, good conductors are going to have low resistance. So metal, copper wires, electrons are going to want to flow really well. Now, if you were to put a bunch of styrofoam on in the line of electricity, that's going to be a great resistor. It's going to slow down the flow of electrons because styrofoam does not do a good job of conducting electricity. And we measure resistance in ohms, OHMS, ohms. And we'll talk more about how to do those calculations later. So a couple things that influence resistance. Let me move my face here, classic. We have 4 things to keep in mind. Just kind of a quick bullet point list. The material of the wire is a great one. For example, aluminum and copper have low resistance. Therefore, if you want a lot of electrons moving through the wire, a lot of electricity, those are 2 good options. That's going to have a low resistance. Thickness. Typically, the thicker the wire is, the lower the resistance is going to be. And the reason being, there is more room for those electrons to move in a bigger wire versus just a little small wire. Length is going to be another one. The shorter the wire is, it's going to have a lower resistance. And that is just because if the wire is really short, there's less room for the electrons to move around, so we're going to have lower resistance. And temperature. Typically, lower temperature has a lower resistance, and this is even something you'll see, in the winter time. You get shocked a lot in the winter time, and don't really get shocked a whole lot in the summertime. So the lower the temperature has, lower the resistance. And we're on to voltage. We've talked about resistance. We've talked about current. We're going to talk about voltage. Voltage is the measurement of energy given to the charge flowing in a circuit. The greater the voltage, the greater the force or the pressure that drives the charge through the circuit. And we'll make an analogy here in a second. But essentially, the more voltage we have, the more drive that we are going to put into moving those electrons through a circuit. So the higher the voltage, it's going to increase the amount, or typically it's going to increase the amount of current that we get. Okay. So there's the difference between volts and amps. It might be a little confusing. Think about it as like a garden hose. So you're watering your plants or watering your garden. Amps are measuring how much water comes through the hose, so how much is flowing through the hose. Volts or voltage is going to measure how hard the water comes out of the hose, or essentially the pressure. Think of it as like the pressure. I mean, if it's coming out of the hose really fast, that's going to be a lot of volts, a lot of pressure. An amp is just how much is coming out. All right, so that's it for this video. I'm going to do a very quick video on Ohm's law calculations. Oops, after this. But what I would say very quickly, and this will end the video, is write down this equation right here. This is called Ohm's law. It is where we look at how to calculate resistance, voltage, and current. So the formula is resistance is equal to voltage divided by current. And watch my second video if you need help with the calculations. Thank you guys for watching. Have a great rest of your day.